I'm going to talk about SIMULIA and simulation in the world of life sciences. Tell you a bit about me first. Well, it's not that much of a rumour. I mean, I've prepared to put it on the first piece of my slide. I've been working full-time in simulation since '88. I built my first finite element model in '87. So I've been doing it a little while. I've worked almost exclusively, we got more kind of noise from next door, yeah. I've worked almost exclusively with products that are owned by DS. So the very first part of my career was with a British FE code. After that, I worked with a program called Cosmos, and latterly, almost exclusively with SIMULIA products and the Abacus solver in specifics. I'm the technical director at the Centre of Simulation Excellence in the UK for all things simulation. And I also do lots of kind of outreach work, so not just kind of running a team and kind of working on advanced simulation specifics, but I also kind of get out there and try and write articles for magazines and give talks and things like that. And I'm also possibly the worst racing driver you'll ever meet. That's me. I kind of got all the gear, but in terms of knowing what I'm doing, I'm not particularly good. So that's what I spend my hobby time doing. Why do I think I'm qualified to talk about life science simulation? I haven't spent my entire career working in life sciences, but I've done a good deal of work in this area. The first kind of qualification to talk about life sciences was very early on in the early 90s, I think 92, 93. I started work on a project with a local university, which usefully happens to be Oxford University, looking at how these are essentially, I bet nobody can work out what these are. Anyone ride a motorcycle? It's a leg fracture. So this is a motorcyclist tibia, and this is a really, really early example of patient-specific data, because this is taken from a scan from some poor motorcyclist who broke that bone, had an external fixator fixed to his leg. So what we did is we built a finite. I could talk about this all day, all right? So some of the other people want to talk about other stuff, I guess. We built a finite element model, patient-specific, in about 92, 93 of his fracture, and then we monitored it as it healed. And then we put a load cell on his leg, and we measured what the load going through this was, and worked out how that influenced the way in which the body responded to the load and built the bone callus. It was a really, really interesting project. Right, I have to be really careful. One of the surgeons in the project wanted an unbroken bone measurement, so he got his friend to put 2 steel pillars in his leg on the bench and put a load cell on his own leg, jumped around and data logged himself. That's how committed. We think we're committed to what we do. These guys are crazy committed. So I've done that. I also wrote a bone remodeling algorithm. So I wrote some software that kind of handled what the stresses did and how the body responded to it. And there's kind of more of that stuff right at the end if I get time. I've worked on a number of simulation projects for very large life science corporations. I guess all you guys are really enthusiastic with non-disclosure agreements when people work with you. So the biggest restraint I've got on what I'm going to talk about today is the fact that no one in our industry, or in life sciences industry, lets us talk about what we do. I was a project coordinator on a thing called FENET, and my proudest thing, the best model I've ever built, and I'm not allowed to show it, is I've built a finite element model of a child's spine growing. And that is a fantastic thing, but the surgeons won't let me show anybody, which is another typical theme for what we're doing. So that's why I can say stuff about life sciences. So what I was going to do for a few minutes is talk about the Simulation Centre of Excellence. That's the team of the Simulation Centre of Excellence. As you can see, they're not particularly enthusiastic about being photographed. They're possibly the best Abacus team outside Providence. They are incredibly talented bunch of people, just look like they're about to be shot. So essentially, the Centre of Excellence focuses on the organisation that was SSA and SIMULIAN, the simulation group at Intrinsis, and then some other people around the TECHNIA group. We're 100% focused on simulation, and specifically on simulation driven by the SIMULIA products by DS. We don't do anything else. And what we're really focused on is the kind of top end of simulation where problems get difficult. The kind of design simulation market where people will kind of use a CAD-based, very simple system isn't where we operate. We tend to operate away from that, although we do quite a lot of work around educating and teaching people in that space. We're really big on automation. One of the big things that in our whole industry is that simulation models take a long time to build. The big joke that all the surgeons thought about the guy with the leg is that he started to heal quicker than we could build models. So, and in the end, they're saying, the surgeons are saying, he's even forgotten he's broken his leg by now, and you're still working on like 3 weeks in. So essentially, that's the big issue with simulation models. They're high effort, they're high reward, but they take a lot of work. So one of the things this group of mine, specifically these guys, have done is work on automation techniques that allow you to build, solve, and identify the results from simulation models incredibly quickly. And we've been in other industries. We do a lot of work in motorsport and in automotive. We've been able to collapse model generation timescales by a factor of, say, 10, which allows you then to explore the design space much, much more. So I'm still only on the second slide here. So we've got 3 offices in the Simulation Centre of Excellence in this specific group. And one of the really nice things about getting in kind of on board with TECHNIA and becoming part of the TECHNIA family was that when Jonas put these kind of 4 points up and these 4 kind of views on the world, they were already things we were doing. And this is how my group worked. So this has worked very nicely as a kind of integration. I talked about outreach. One of the really important things, if you're going to do simulation, is to explain what you're doing, explain how you're doing it, and kind of get the message out there. So we've done a lot of work in just simplifying the learning process, working the learning curve, and trying to kind of widen the application and applicability of simulation techniques. And we do that by kind of constantly going out there with this sort of webinar, tutorial, just learning material, knowledge-based. So when I'm starting a presentation at a university, because I quite often go and give intro lectures, I talk about the person who invented all of the science that goes behind the simulation tools we use today. There was a guy called Robert Hooke. He lived 17th century. He lived in Oxford and lived in London. He was the first person to associate an equation with something that happened in the real world. So he was the first person to come up with a simulation. This simulation said, if we know we're going to pull a spring, we know how hard we're going to pull it, we know how much it's going to deflect. He was predictive, and he was the first person to do this. So he's a really, really clever guy, and you've never heard of him, have you? Have you? No? There's a reason. If you haven't heard of him, there's a reason you haven't. So anyway, he did a load of work on springs, and this is his science. You'd be glad to hear this is the only equation I'm going to put in this presentation about simulation. They're apparently halve your audience. Every equation halves your audience. So, but the bloke who invented simulation and the finite element method was a life sciences freak. The thing he was really interested in was life sciences. He was the first person to describe the cellular nature of biological structures. So he was the first person to look at multi-scales. So the guy was an absolute genius. These are some of his drawings. So he identified that materials have a lower scale, smaller scale structure. This is right. They were still burning witches at this point, and they really were. So he was very lucky he didn't get himself into trouble. So he also was the first person to describe the concept of a smart material. He wanted to invent an artificial muscle. So he died in 1703. So he described an artificial muscle, and he did it by looking at the natural world and drawing things like this. He proposed the idea of a finite element model. He was the first person to come up with the idea of developing a structure out of springs, and he beat Newton to publishing about gravity, which is then Newton spent the rest of his time rubbishing everything Hooke had ever done. He may even have built a flying machine in Wadham College in Oxford. So the guy was a genius, and he did it all before 1703. So the point of this is that life sciences and simulation have been kind of joined at the hip absolutely since day one. So what we'll do, or what I'll do, is I'll just talk about some of the things about general simulation market, and then we'll look at how those apply to the life sciences market. So essentially I've got 2 models. I've got possibly one of the simplest simulation models and one of the least simple, one of the most difficult simulation models. This is a friend of mine's car. It's probably one of the least ecologically viable vehicles on the planet. The only thing that makes it ecologically viable is it's only moved about 3 miles in the last 2 years. So it's not really causing much of a problem. But anyway, right. So what do you use simulation for in the general market and engineering? You identify things that will work and things that won't work. You find out why this car works. You find out why that bracket might break. We use that to be efficient, and we use it to reduce the amount of testing we do in our development process. That's really important. So the cost saving, because simulation costs, it's not a cheap thing to get into generally, but the cost benefit is in reducing testing. But not only do you reduce the tests, you understand your tests a lot more, because if we're looking for where to put strain gauges, where to measure things, we know it's here. If we want to know what's going on in the airflow, we know all the important stuff's around here. So simulation improves testing. But other than that, the big benefit is we build a body of knowledge. John Kitchenman was talking about locking in and kind of locking in the company's IP and the company's knowledge. And simulation is possibly the best tool. You build a simulation model, you understand it. You understand it, you can write it down, you can lock your IP into your company and own it, which is what that says. So the other thing is compliance. Plenty of people like the FDA, people in the oil industry, they make you do FE. So it only works really if you make it an integral part of the design process, which is why working on the platform is so good. Simulation on its own as in a silo is a great thing, but it's not as good as when you couple it into the design process properly. It's got to be fully supported by test programs, otherwise you tend to lose your way. It's got to be managed properly, because if you don't, people just have fun. That's what happens. You leave a simulation engineer in a room, he'll just have fun. And we've got to do it, organise it so we deliver results in an appropriate time frame. So I was really pleased with this line. Simulation technologies just don't do good stuff because you've got them and because you do it. They have to be managed and they have to be an intrinsic part of the design process. So why would we do simulation in life sciences? Identify designs which don't work, reduce the amount of testing, improve the results of testing. This is looking like a familiar list. There's nothing special about doing simulation in life sciences in terms of why you do it and what the benefits are. It's all the same. The drivers and even the techniques are generally the same. But you meet a surgeon, he'll say, oh, but what our problems are properly difficult, they're properly kind of technical, and they're not like the sort of thing you work on. And you spend half your time trying to convince them that they really are. So the special challenges in life sciences, and there's an abacus model of a skeleton operating, which I rather like. Biomaterials are very complicated. We already looked at the fact that in 1680, 1690, Hooke had identified that biomaterials are very cellular, very complicated. The materials that we're allowed to use can be very limited. In the implants, you've probably got 2 or 3 steels. You've probably got 2 or 3 metals. You've got a subset of plastics. So the challenges are all about material choice. Needless to say, if anyone's worked in structural analysis of biostructures or implants or anything, loads of environmental influences are phenomenally complicated. Interactions are critical. Interactions between parts is a very difficult thing for a simulation tool to do, and we might get into more than one physics. So we'll look at structures, we'll look at fluids, but you might end up having to look at coupled things. So the other problem is geometry can be very tough to capture. Getting hold of the actual shape of a life science structure, like a bone, like a... I actually drew a parametric femur once that was completely controllable, but the way in which we generally tend to do it these days is through scanning, and there are sort of products to do that. But all that means is all those things mean you have to have the best solver technology out there to even start to think about these things. So things we've worked on joint replacement. That's an absolutely standard life science. Looks like it's coming upside down, but it hasn't. So we've done a lot of work on knees. We've done in our group some fantastic work on a knee that we're not allowed to talk about. We've done a lot of work on the kind of durability of hips. And one of the projects we got involved with was an elbow for a dog. So there's a load of structural domain stuff which is like the motorcyclist thing. You're trying to use lumps of metal to replace or enhance the kind of action of bits of the human body. This is quite simple structural stuff. This is what I was doing in the 90s in the life sciences world. It's really interesting. It gets very complicated around the knee because, as you can see, basically there's a lot of movement and you're tracking very complicated interactions. So just go back again. I seem to have gone. Yeah. So the knee gets very complicated. There's some really, really nice stuff in the kind of world of the 3D experience to do with sportswear. So anything involving the kind of action of a sports shoe and the way in which the foot interacts with the ground. Then there's a lot of work on, we're going back to this kind of Hookean cellular solid approach, where you can see that we've optimized the sports shoe with different cellular properties all around it. And the system is kind of using optimization techniques to work out how to give this interaction the best time, the best kind of influence on your foot so that you can run as fast and as far as you can. So structural domain is really well kind of sorted. There's a whole load of science around stents. If stents are really difficult, these things are impossible. I mean, everyone knows what you do. You kind of make a little hole in someone's leg and you push this thing up and it goes into the heart and you use it to stop kind of collapsed arteries collapsing. So somehow or other, you've got to get this thing into there, and when you get it there, you've got to deploy it and make it do its stuff. This is really, really difficult, and we do quite a lot of work on this stuff. They use really exotic materials. They use shape memory alloys. They're all nitinol, and that stuff is the bizarrest material you've ever come across. If you know about stress-strain curves, it goes up, along, up. It's a very, very odd thing. Anyway, so stents, we do a ton of them. They're a really interesting part of the simulation world. You know, you should never put a slide up which you don't understand. This is my slide I don't understand. This is all to do with electricity. And as you can see, I'm the son of an electrical engineer, but that sort of thing's not genetic. So I don't understand much of this stuff. This is to do with kind of field densities, and this is to do with a product called CST. I've got no idea what's going on here, but it looks quite interesting. This is a whole different physics, and the point of putting this stuff up isn't to kind of highlight my lack of knowledge of the world of electricity. It's to talk about the fact that simulation works across a whole load of domains. We work in the structural domain. People like me have worked that domain forever. There's a whole load of electrical domain stuff, which is all to do with compliance and all the same rules apply. You can save money, you can develop IP, all of these things work the same way. I just don't know how. There's a fluid domain. The fluid domain gets really interesting. This is, as you can see, my hobby was kind of looking at how racing cars behaved. Single domain fluid problems aren't that common in the SIMULIA world. I mean, there are some. These are all kind of blood flows around blood vessels in the body, and essentially stenting is around controlling this where things get too restricted. So you got physics that's structural, you've got physics electrical, and you can see where I'm going with this, can't you? And you've got physics that is fluid domain. The really interesting stuff, and where a product like SIMULIA really comes into its own, is when you've got one sort of physics and it's controlling another sort of physics, and that other physics is controlling that. So you go around in this really vicious circle. And life gets really very interesting. If you look at what's been going on in the world of SIMULIA, they've been kind of populating this matrix of different physics, structures, electromagnetics, fluids, thermal, and some others. And then they've been populating the length scales, which allows us to build up a representation, especially in the world of life sciences, where it's phenomenally important, of a lot of things that are going on. Because what happens is that some problems are obviously structural. The bracket's obviously structural. The car's obviously a fluid problem. But there's a whole range of problems, certainly in life sciences, where, and hopefully the video's working, where the physics talk to each other and interact. So we've got a structural valve there, and we've got the flow through it. I'm not entirely sure I believe this, frankly, but basically you can see how the flow is interacting with the valves are interacting with the flow, and we've got a model of a heart valve by combining the different physical domains. So what's the ultimate combination of the physical domains in life sciences? It's this thing. You can see this model is quite complicated. So there's the mesh. No idea how long it took to make that mesh, but it's quite complicated. It's a work of art, if you like. If you like this sort of thing, if you like a mesh, that's a good one. Then there's all of these kind of fibers. There's an electrical system, there's a fluid system, and if we can combine all of the physics that control the human heart, we can create a fairly credible model of the heart. This is, I say fairly credible because this is an early one. I've got some pictures of some later ones. And all the same rules apply. You can use it to test things out. You can use it to save you money in development programs. You can use it to understand more about what's going on when your device has to interact with the human body. It's not often that you get to see a model development process. No model should ever arrive fully formed in someone's kind of machine. They should start off simple and build up. And you can see on this that there's a really, really simple heart model. Doesn't even look like a heart. Then there's the first one I ever saw, which is kind of proof of concept model. Then they added electromechanical kind of actuation to it. Then they kind of add some really clever stuff around fluids, and then some really, really clever stuff about what happens to the heart when you do various things to it, like drug interactions and things like that. So you go from a very simple model to something that you can automate and you can deliver really useful results to save money in trials and learn more about what's going on. Because plainly, it's easier to investigate in a computer model what's really going on than it is in a real model. The real model happens to be a bit more accurate, a bit more realistic. The computer model is easier to interrogate. So what have they used this for? Try and keep an eye on the time here. Well, my mum's got one of these. This is a pacemaker. Mum's pacemaker is about the size of a 50p piece. You know, they also data log every heartbeat. When she goes to the doctors, they can say what was happening on a given day. But the first application of living heart was you have to have these wires put into the heart, and the pacemaker shocks it and makes it work. So the first application was actually making sure that these things didn't fatigue and worked properly in that environment, saving lots of experimentation and therefore money. It's done by Boston Scientific. The next thing is to add proper fluids to the heart. You can see, if you're lucky, actually this heart is actually pumping real fluid. These are two CFD models. This is getting serious. It's getting to serious supercomputer technology. You can't solve these things on anything less than about 128 cores. You're getting into serious compute to run the heart. So, why am I talking about this stuff? Because complex problems need capable solvers, and Abacus is generally known, the SIMULIA product is generally known to be the most powerful FE solver out there. Certainly it's one of the top 2 or 3. It's a fantastic piece of software. But the argument is that I'm going to make is that you don't just need that sort of level of solve power to do a heart. I'm clicking here and nothing's happening. There are plenty of other medical device scenarios where the physics is very complicated, but you wouldn't think so. One of these classic areas is a snap fit. Snap fits, auto-injectors, they're all full of little devices that fire. And the finite element solution of those is very, very difficult. So if you look at this, if I can make this animation work. Oh, there we go, it's working. Miracle. That isn't as complicated as a human heart, but it requires the same sort of solution technology to give you an accurate and routine result. So if you're going to roll out the simulation of medical devices and the design of snap fits and auto-injectors and that sort of thing, having a SIMULIA level solver is about the only thing that will give you an answer regularly, reliably, and with no drama. So not only do you need a decent solver for hearts and fluid structural interaction and the like, you need it for everyday design problems. So adventurous projects need decent software. Day-to-day simulation tasks in this space also do. And you can only really kind of widen the applicability of the simulation work you do, because essentially it will pay you back if you get more and more people to do it. You can only do it if you use the right level of solver. So that's my point. And if I got enough time, I was going to talk about one more thing. So we've talked about engineering techniques being applied to life sciences problems from day one, but that is the direction of travel. I bet no one knows who that is. Someone in a training course knew who he was the other day. He is called Julius Wolff. When you go to space, do you know what happens to your skeleton? Your body absorbs your own skeleton, which is why they have exercise bikes in spaceships. Julius Wolff, again, pretty early on, realised that this was a thing, right? There it is. He starts to describe it here. I wrote a Julius Wolff's law simulator in about the mid-90s. It's written in C, and it's all quite complicated, and it impresses the team that their boss used to know how to program at one time, which is quite a useful thing. It's useful just for that. So if you do what I did, which is write a piece of software that mimics what the human body does, and where there's load it puts material, where there isn't load it takes it away, you end up with something that reveals structures like this. It's called a topology optimizer. They were invented in Chicago around the time I did mine, and then someone realized if you put a real component in it rather than a bone, it would optimize a structure for weight and efficiency. This is the whole birth of the program called topology optimizer, or the technique called topology optimization. And we're going to round up by saying that if you look in GDE, the Julius Wolff's law simulator is applied to real structures inside the 3D experience platform as a product. So the direction of travel hasn't been just mechanical to life sciences. The life sciences work has fed back into mechanical design.